Okay, so like normal subgroup in group, right? You have this ideal. So what does it mean by ideal? So you have an additive mean plus, right? Under addition. Okay. And additive subgroup N of a ring R. Why we have to say this? Because a ring has two operations, a plus, addition, and multiplication. Okay, so once, whatever you write a statement, you have to think why you're writing it, why the condition is there. If you read a theorem, why it's given, da, 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 da. Whatever is given, it has to be used. If not, you won't give extra condition, right? So N is a subgroup under addition. Because to be a ring, it has to be a group under addition, right? Okay. Satisfying the properties, right? So AN is a subset of N, and B is a subset of N for all A and B in the ring. Is an ideal. So you remember last time I went through some examples on ideals, right? And what do you mean by subset? This went back to when you first learned sets, right? I don't know where you learn sets. In my university last time, they call it Introduction to Higher Mathematics. In UTM last time, they have this set theory and logic. They learn this. And they also have discrete mathematics, which says that if A is a subset of B, this is the same thing as saying A in A implies A in B. So this is what subset means. Okay, A is a subset of B. If A is in A, then A is in B. So when we go and you want to do the proof, you don't use this, just this, but you use the element. And then when you write your proof and make sure that you distinguish between set and also element. Yeah, element, you just use this as an element. So that is how I use this in my previous class to show that it's inside, right? If you go back and see, I take one element in A, I take one element in N, and then I show that this is an element in this N. That is how you have to show it. Okay, so for this chapter, instead of just ideals, okay, we had to find prime and maximal ideals. So just now I put a subgroup, right? So example, before we go to the rest, suppose the ring R is this a ring? Then you have to look, it's a subgroup, right? It's a group, right? And all the properties of a ring. Hana is a ring, right? And the unity, that's a unity 1, because 1 is inside here, right? Okay. You know, in the last Viva, I remember, that's this student, right? Because she followed the one in the original paper. Okay, the original paper give like this. And then the examiner said at least there has to be 2. Or if it's better, 3. So you can see the pattern before you go to the end. If you just put like this, you don't even know what's the pattern, right? It can be 0, 3, 5. Okay, remember that. Even you got from somewhere that gives this. You can change accordingly. And this dot, 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 it has to be 3. Okay, so if multiplication, it has to be in the middle. If you put that's down there, right? This multiplication dot in the middle. Because if you put, this is 1 point times 2. If you put down there, it's like 1.2. So these little things take into consideration when you write a paper or write your thesis or write your dissertation. Okay, anyway, okay. Can somebody give me an additive subgroup for this one? One is, you remember this one? What's the subgroup? 12 is, right? So you have 2, right? And then 3, and then 4, and then 6, right? This is the subgroup lattice of Z12. So this went back from group theory 1 actually. Okay, now my question is, if you look at the definition just now for ideal, okay, additive subgroup of a ring, right? So question is this an ideal? So there are 2 things you have to check, right? And you see, since this is a commutative ring, right? Because numbers, A times B is B times A. So these 2 will be, just check 1, right? Okay. So if N is this, for example, which is, what is 2 actually? Let me put, where to put? Right? Okay. If you multiply anything from Z12, if it is from here, you multiply, of course, it will be back in here. Like you multiply, if A is into, of course, A times this is in here also, right? Because it is close, right? Because it is a subgroup, it is close. If it is outside, like 1 is not in here, you multiply, you get back 3. 3, you multiply, you get 0. 3, you multiply, you get 6. Multiply by 3, you get 0. Multiply by 3, you get 6. Multiply by 3, you get 0. Multiply by 3, you get 6, which is inside. So this is an ideal. You can check. This is also an ideal. This is also an ideal. This is also an ideal. Let's check maybe 6. Let's check 6. So the answer is yes, yeah? Okay. So six, and then done, right? Because 12 is 0. Okay, there are not that many things to check. Okay, if you multiply 0 by 0, it's just 0. 0 by 6 is 0. You multiply by 1, you get 0, 6. You multiply 2, you get 0, 0. 3, you get 0, 6. 4, you get 0, 0. 5, you get 0, 6. 6, you get 0, 0. So it's always only 0 and 6. Yeah. So it is back inside, left and right. So you see, for this one, you can actually generalize. For cyclic group, right? The subgroup is the divisors, right? For the order. Right? So this is an ideal. Now, with this, we have improper ideal and trivial ideal. Like you have improper subgroup and trivial subgroup. So when I say it's improper ideal, it's the whole R that is improper ideal. If I say it's a trivial ideal, it's just the 0 subgroup. Okay. Okay. If I said it's a proper non-trivial ideal, proper non-trivial ideal will be that, right? So this is like the subgroup before. This is the improper ideal. This is the trivial ideal, right? And the one in the beginning is the proper non-trivial. This is specifically for Zn of cyclic group, but it does not apply to all rings. Okay, for some other rings, with some other multiplication and addition property, you have to check. Okay, so that is the first paragraph in the first page. Okay, look at the theorem. Theorem 10.1. Okay. If R is a ring with unity, let me see, my students are still there or not. Empty none? How are you, Empty none? Can you define what a unity is? If R is a ring with unity.
1.
What does it mean by unity? Yes?
1. 1.
1. Or a
Element, there is
multiplicative identity.
Yes.
It's not necessarily 1,
Yes.
yeah? Okay, so if R is a ring with unity and N is an ideal. Okay, because not all ring has a unity. So if you are given something like this, you think why they give you that? Because not all ring has unity. That's why we have just ring with unity, right? Like the even numbers, they are ring, right? Even numbers, but they don't have a unity. There is no one if it's even numbers, but it is a ring. It's a group, right? For odd numbers, it has one, but it is not a ring because the 0 is not there. It's not a subgroup or not a group, right? So you have to think ahead. Don't just this. You have to think why you are given that. So R is a ring with unity. So then you know that even set of even integers are out because it doesn't have a unity. So if you have a matrices, unity will be identity matrix. So when you say 1, that's not necessarily, right? For matrices, maybe that's identity. Okay, if R is a ring with unity and N is an ideal containing a unit. Okay, Vian, are you here? Vian, are you here?
Yes, Prof.
What is a unit? What is a unit?
Equal to 1.
Unit? No. Unity is the identity under multiplication. That's unity. What is a unit? A unit is an element that has an inverse, right? Okay, so you imagine R is a ring with unity. We call it maybe 1, or it can be an identity matrix. And N is an ideal containing a unit. Meaning if you have A, there is A inverse in there, then N has to be the whole ring. Okay, so the proof follows from the definition of an ideal and having a unit. This means you cannot have a subgroup, additive subgroup, that contains the inverse, elements with inverse, if it is not the whole ring. You cannot have just a proper subgroup. This is what it means, okay? Meaning if you have a big one, R, and then you're given a set that has inverse also inside the subset, it has to be the whole thing, okay? So this is what it means by this theorem. So if you go and see the proof, okay, let N be an ideal. I don't want to erase this because I want to use this later, that's why. Okay, so look at the proof. You have to start the proof with, let R be a ring with unity. At the proof, I didn't put that, but that is what is supposed to start with. Let R be a ring with unity, and N is an ideal in R. I put N is an ideal in R. And suppose U is in N, a unit. Okay, so suppose U is in N, a unit. Now, using the definition of the ideal, since U is in N, right? Now Rn is in N for all ring. I don't use U yet, since N is an ideal, okay, any R multiply N is a subset of N. Now take R to be the inverse of U. Take R to be the inverse of U. U is in N. Okay. Then you multiply U inverse and U is in N. Here, you replace, right? R is U inverse. U is in N, you multiply by U. This is 1. This is 1 is in N. Okay, we said R is a ring with unity. So 1 is in N. Okay, but we have Rn is in N. So we have the other way around. This one is definitely in here. This one is definitely in here. Okay, so R times 1 is R is in N for all R, right? So at the end you have this R times 1 is in N for all R. And this means N is R. Okay, so this is quite a straightforward proof. And this is what people in algebra do in the research to prove something. You start by assuming this condition. This is what you want to show. If you cannot reach this by whatever condition is given, you add more condition. That is how they start this. First, they start with just a ring with unity and N is an ideal. And then this is the extra condition, containing a unit. So containing a unit means you want to multiply. And by using the definition of the ideal, that's why there is an N is an ideal. So at the end, you want to show N is R. So before you even understand one proposition or theorem or property, you have to know why it is given and what it means by the proposition. You don't just give it or use it because it's there. Okay? Okay, next. A field contains no proper non-trivial ideals. A field contains no proper non-trivial ideals. Proper non-trivial ideals. What does it mean by a field?
The field, the ideal in field just the field itself also the zero. The zero ideal.
How do you define a field?
R with the addition abelian group, also R star without identity with the multiply abelian group also.
Okay, and a field is a set with each element, each non-zero element is a unit, right?
Yeah. Yes.
Meaning each element has an inverse, right? Okay, so
by theorem 10.1.
Yes. Okay, before we prove, now can somebody tell me what it means by corollary? Why you use corollary? What does it mean by what? Ain. Why?
As a result for theorem.
Wait, Mariam. Okay, I ask Ain first.
Yeah. It's a result from a theorem.
It's a direct consequence of a theorem. You call it corollary, right? And why we call it theorem?
As we have proved it.
Theorem is a statement that is probably important enough that we call it a theorem with a proof. Okay, if it is not important enough, everything is important, but we don't take it like so big. We call it proposition. All right, so make sure when you write, you know what it means. Proposition, corollary, because it's the direct consequence from the theorem. Also, we have lemma, right? Lemma is also a statement with proof, but normally lemma comes before theorem or proposition, and we use in the proof. Okay, so when you write in your thesis or dissertation, if you want to put lemma, is your lemma, and then there is a proof, and it comes before theorem. Okay, somebody's lemma can be your proposition, because you probably don't take their theorem, you just take their lemma. So their lemma can become your proposition. When you copy, you change the name. Because when I see lemma, I will think that it's your own with proof before theorem. Understand? So you can change the name. That's the point. Okay, from their lemma, because they have their theorem, but we don't want the theorem, we want the lemma only. So you want that result. You don't put as lemma, because then people will see where is the theorem. So you call it proposition. Okay, so now this contains no proper non-trivial ideal, because from here, every element is a unit. If every element is a unit, you will get is equal to R, right? It's equal to everything. So it has to be, it will go to improper. Or if there's nothing, that's just 0. Okay, now we go to the maximal first, yeah? Okay, maximal ideal. A maximal ideal of a ring R, okay, of a ring R, call it M, maximal. We don't want it equal to R, is such that there is no proper ideal N of R properly containing, you know English? They say English and Arabic are similarly difficult. But if you talk in Arabic, you think Arabic is easy. This proper and this proper are not the same proper. This proper is mathematics proper. This proper is English proper. So it means that if you have M, right, an ideal, you won't get anything in between. You won't get like this. You won't get this N, right? So there is no proper ideal N of R properly containing, properly, yeah, I can say it's math proper also, but this is not. So we want proper, right? Okay, we want proper. Because maximal ideal can be the whole ring. You don't want anything in between, okay? Now, can you tell me which one is maximal then here? Who I haven't called yet? Wali, are you here, Wali? Wally, are you here? Lava, I haven't called you today.
Subgroup 2 and subgroup 3.
Question is, which one is the maximal ideal here? Subgroup generated by 2 and by 3. Okay? So this is maximal, this is maximal. You don't see anything in between, right? This is not maximal because there is this. This is not maximal because there is this. Okay? Because I give earlier that they are all ideals. Okay, we can go through the example. Okay. That's a nice theorem that don't use definition. That's why most of the time it is not easy to prove by definition. So people came up with a theorem or property to make it easier to prove using the property or theorems, not directly by definition. Okay. So I will write this theorem. Okay. Let R be a commutative ring with unity. So I need the unity, the one. Then M is a maximal ideal of R if and only if R mod M is a field. Okay, it is much easier to show that the quotient is a field than trying to see whether there is a bigger ideal in between to show it maximal. If the group is like this, it's easy. Cyclic, and we can see the factors, right? But in some other cases, you can check whether it's maximal or not by looking at the quotient. Okay, if the quotient group is a field is a ring in which all elements are non-zero elements are unit. Okay, I won't go through the proof. You can go through one by one. One is maximal, one you assume commutative ring with unity, and then there is a coset, and there's the homomorphism. Okay. In Dr. Sanhan's class last time, he mentioned a little bit about this. Now I give you one example. Okay, I don't need this example. Oh, what about the, what they call it, EPPP? Is it already open? I forgot already the date. Anybody know?
Not yet, Prof.
Not yet. It's in June, right?
Yes.
Okay. Because I saw last time a poster, but I forgot. Okay, 10.2. Since okay, Z mod NZ. We have seen this before, right? Z mod NZ is isomorphic to Zn. Okay. So, and you know, Zn is a field if and only if P is a prime.
And
Just now, Z12, it is not a field because not all elements is a unit, right? Let me see. Let's look at Z4. Right? So the non-zero element, this, the inverse is this, 1 times 1 is 1, okay? 3 times 3 is 1, right? 3 times 3 is 9, which is 1. Okay, so this is the inverse of itself. 2 times 2 is 2 times 2 is 0. You know, mathematics is weird, right? The higher you learn mathematics, 2 times 2 you say is 0. It's not 4. Okay, so there is no inverse for this one, right? 2 times 1 is 2. 2 times 3 is 2. 2 times 2 is 0. So this is not a unit. So this is not a field, right? But if you look at Z3, 1 times 1 is 1. 2 times 2 is 1. What is mathematics? 2 times 2 is 1. Okay, if you go through Z5, okay, not 0, 1 times 1 is 1. 2 times 3, 3 times 2 is 1. 4 times 4 is 1. You see, all element is a unit. So in order to find whether this is maximal or not, so that is why I have that the ideals, the maximal ideals, right? The maximal ideals for Z, okay, this is the answer. The maximal ideals, if I change the example to a proposition, right, I will write like this. Let R is Z. Then the maximal ideals of R is P Z. P prime. You remember just now when I put Z12, right? The maximal ideal is the one generated by 2 and generated by 3, right? Those are the prime, okay? Because otherwise, how do you show that this is the maximal ideal by definition? Right? You want to show there's nothing in between. So much easier if you show the quotient. The quotient is a field, right? Okay, so that is example 10.2. Next is the corollary from, I think, theorem 10.2. Yeah, I can give you a question and you can actually use this theorem or corollary, okay? And since our test and exam is open book, you can refer and mention the name of the corollary or theorem if you want to use it. Understand, right? Okay. Corollary 10.2. a commutative ring with unity is a field if and only if it has no proper non-trivial ideals. A commutative ring with unity. So you have to have commutative ring, meaning matrices are not, because most matrices, they are not commutative. If you don't have a unity, you cannot consider this also. Okay. And how do you show it is a field? If you have no proper non-trivial ideals, or the other way around. If you already found this, then if it's a commutative ring with unity, then you can show it is a field. So it's both ways. Okay, whether you want to show from here to here or from here to there. Okay. That is an example that I give you there. Example. Remember this, yeah? For a ring, maximal ideals is in this form, PZ. That's the next. This one did not say about maximal. This one just say about whether it's a field or it's about the ideals only. Okay. Now this is interesting. All ideals of Z are in the form of NZ. Because we want to multiply, right? Remember, AN is in N. So if it's in this form, you can just rewrite. So if you have integers Z, 2Z is an ideal, 3Z is an ideal, 4Z is an ideal. All the PZ will be the maximal ideal, right? Okay. So that is what it is in the example when PZ is the maximal ideal. Okay, now we go next. I should change the chapter title, yeah, Hannah. Please help me. Next time it will be maximal and prime ideals because I normally will go through maximal first instead of prime and maximal. Okay, we go to the prime ideals. Okay, just do with the singular prime ideal. Okay. And ideal N, we don't want to be in equal to, so just a proper subset. In a commutative ring R. So cannot be equal to the whole thing, right? We want to be proper, not improper. Is a prime ideal if AB is in N implies A is in N or B is in N for A, B in R. If you have 2AB in R, if their product is in N, then either A is in N or B in N, or means can be both, right? Remember the or, it can be either one or both. Okay, so if A is not in N, B is not in N, you cannot multiply to get it in N. That is another way to look at it. Okay, so this is called a prime ideal. And if you see this, it's not equal to the whole R. Suppose your R is Z. N is trivial. There's only 0 in N. So if you want AB to be in N, AB has to be 0, right? And if AB is 0, A has to be 0, or B has to be 0, or both are 0, because that's the only thing that is 0 in here. Whatever multiplied to get 0 in Z has to be 0, right? In integer, you want to multiply integer times integer equals 0, has to be either this 0, or 0, right? Which is in N. So this is what it said there, that this is a prime ideal. Example, yeah? A prime ideal. Trivial subgroup. Okay. Now we go back to my previous example Z12. I already erased. I wish I don't erase, but let's see. Okay. So okay, just now remember we have this is generated by 1, right? And 2, and 3, and 4, and 6, and 6. Okay. Now we don't want this R. Why do I have 1 there? I don't want a 1. I'm missing a 4, Hannah. Can you correct that? The ideals, yeah? 0, 1, 2, 3, 4, 6. This is the ideals, including the trivial and improper. Okay, that's the ideals. Even 4, right? Because you multiply anything else, 4, 0, 4, 8. Right? You multiply, say 2, you got 8. You multiply 2 times 8, it's got 4. So this is also an ideal. Okay, now what are the prime ideals? And turns out that the prime ideals are the same as the maximal ideal. For example, you see if you wanted to get 2A times B, is in here. You see, what do you want to multiply to get a 2? in Z12. Can you get and multiply any 2 in here to get a number 2 if they are not from in here? You can actually easily see from the Kelly table, the multiplication, right? It has to be from in here to get a 2. If you take any like 5 times what is 2? Modulo 12. Okay, so you can go through and try to check one by one. But one way is to get the multiplication table. For this one, it's too big. If you know how to use gap, it's easier. Because you will, multiplication table will be 12 by 12, right? You can start with the small group and see. Okay, in next example, is a little bit different, in which we look at the red product. So this is example. Okay, now the claim is Z cross 0 is a prime ideal. Now suppose we have 2 elements in here, A, B, C, D in Z cross Z. Now you want the product inside this, right? To be a prime ideal. Now when you multiply, you will have AC, BD inside here. So this gives BD has to be 0. So if B times D is 0, they are all integers. This means B is 0 or D is 0, right? So CD, since B is 0 or D is 0, B is 0 or D is, AC is BD, right? AB times CD. Yeah. So if B is 0, then AB will be in Z0. If D is 0, why do I see D here? Oh yeah. If B is 0, AB will be in Z0. If D is 0, CD will be in Z0. So this implies A, CD in Z0 or CD in Z0. Right? That is the definition. Okay. Next theorem, like before, gives you a simple result to see whether it's a prime ideal or not.
Sorry, Prof, I have a question.
Yeah.
When we choose the two elements from the rings, the elements should be distinct or can be the same also?
For A times B, any.
For example, yeah, any.
It can be equal.
It can be equal.
Yeah.
Okay.
We just take any AB in the ring. It didn't say that A cannot be equal to B. Before I have theorem 10.2 that says, theorem 10.2 says, commutative ring with unity, maximal if the quotient is a field. Now for prime, again, commutative ring with unity, and the quotient, if it's prime, it's integral domain, right? Before it's a field, now it's the integral domain. Can somebody tell me what does it mean by integral domain?
A commutative ring with unity that which does not have zero divisor.
So commutative ring with unity is the one that's given. That's why we put that in the theorem. Has no zero divisor. You see why there is no zero divisor? Because of this. So you can actually see how you can prove it, right? Zero divisors means B is not in there, C is not in there, but when you multiply, it's zero. We don't want that, right? We want it to be prime, so when it's equal to zero, either one has to be in that end. Okay. Okay, so that gives directly to corollary 10.3. Every maximal ideal in a commutative ring with unity is a prime ideal. Every maximal ideal in a commutative ring R with unity is a prime ideal. And that is why just now Z12, right? We already get the maximal ideal. They are also prime ideal because that one is a commutative ring with unity, Z12. So this, if you already get maximal, you can get the prime. You get the prime first, you can get the maximal. Okay, so that's the summary there. The summary has to, Hannah, you have to help me. In summary has to move far away from corollary 10.3. Looks like it's part of corollary 10.3. So we have three things that you have to remember. Yeah, you can highlight this or put in the box. This is very important. An ideal M of R is maximal if the quotient is a field. Okay, but all this you can do it if you have a commutative ring with unity. Remember, if I ask you a question, it's not commutative or there is no unity, you cannot use this theorem. Okay, first you have to get that this ring is commutative with unity. If you take the quotient, it is a field, then it's a maximal. If you take a quotient, it is an integral domain, then it's a prime ideal. And then you know that every maximal is prime. So the thing here is that you have to know what is a ring, basically, right? You have to know what is commutative ring. Go back to the original definition. What does it mean by commutative ring with unity? Easy, because it has to have an identity under multiplication. You have to know what integral domain is. So if you want to see whether you understand or not, you remember last semester at the very last assignment, I asked you to write to have a Venn diagram, right, in the group. So look back into your Venn diagram and you can see what kind of sets that we have as an integral domain, which is a field which is not integral domain, and so forth. Okay, make sure you understand the basic. So when you are given a question, then you can see how you can apply this particular ring to get the ideals. Okay. Okay. The rest, prime fields, is just about the field with no proper subfields. You can read through prime fields. So a field is called a prime field if it has no proper subfield, no proper in between. Okay. So like ZP is a prime field because you cannot get a proper, right? Because it's already prime. There's nothing in between. Q is all the rational numbers. How can you get a subset of a rational number? Right? So they are just for you to know the definition of prime fields. The rest, just read through. This is just some other definitions about a principal ideal generated by, it's nothing much. I will repeat this again when in the next chapter, in which I will have the polynomials and also extension of fields. I will go through this again. The irreducible polynomial, I will repeat this in the next chapter. Okay, so as an exercise, you can do that first. Don't send it because you already have something to send in this Wednesday and next Wednesday. But change this, where is the 12? Change the 12 into 24. It's a good exercise. Okay, this is 2 cubed times 3. So the subgroup lattice is longer, right? So you will have, this way you have 2, 4, 8, right? And then you have 3, and then 2 times 3 you have 6, then 4 times 3 you have 12, right? And so forth. So longer. Then quite easily, right? The prime and the maximal is one on top. See, I'm already giving you the answer. The next one is Z2 cross Z4. That is a little bit different. Okay, you can try that. But 3 to find, so it's a field. You can use example 10.8. See if you can try that without I go through example 10.8. Try to figure that out. Number 4, again Z18. So 18 is, right? It's very, very similar to 12. Okay. So you can have the ideals again. 1, 3, 9, 0, 1, 2, 6, right? For that one. Okay, I think that's for chapter 10.